Okay, so now in this video we are going to analyze the correlation between two centrality metrics. Um, the centrality metrics we are considering are the between the centrality and the LCC prime DC. Okay, so in the last video I showed you how to input a graph as it's a text file to the jar program I gave you to compute the centrality metrics. So this output is taken from the jar program for the centrality metrics. So now in the previous videos we saw in detail how to compute the Spearman's concordance and the Pearsons correlation coefficient. So let us now see how to do this with the centrality metrics. So it's the same procedure. Okay, so for rank-based correlation, so here you have the vertices and the betweeners and the LCC prime DC values. So again we'll follow one particular convention, that is giving a lower rank number to a lower centrality value or a higher centrality value. Now again, if you remember on the centrality metrics module, I said that for all centrality metrics we'll see in this course, the larger the number, the better, or the more important is the node for the network. Okay. Alright, so we'll follow this convention that the lower centrality metric will have a lower tentative rank number. So the lowest value is 0, and there are three central vertices with the value of 0. So we have a tie here, and we break the tie in favor of the node ID. So the node vertex 0 will get tentative rank 1, and vertex 6 will get tentative rank 2, vertex 7 will get tentative rank 3. So you have 1, 2, 3 for the tentative rank. And then the next smallest value for betweeners is 0.33, that will be tentative rank 4, no other vertex has 0.33. Then the next smallest value is 2.33 and no other vertex has that, so it's just tentative rank 5. And then 4, no other vertex has 4, so it is 6, then 4.33, 7, 5, 8. So these are the tentative rank values. Now how to get the final rank values? Now for betweeners of 0, there are three vertices with betweeners 0 and that tentative rank values are 1, 2 and 3. So to get the final rank for these three vertices, you have to compute the average of the tentative rank values. So average of 1, 2 and 3, which is 1 plus 2 plus 3 divided by 3 is 2. So all the three vertices 0, 6 and 7 will get a final rank of 2. Now for the other vertices there is no tie, so the final rank is going to be same as tentative rank. Okay, so 5, 5, 6, 6, 4, 4, 7, 7, 8, 8. For LCC prime DC, these are the values for the vertices. So again we'll give the lower rank number for lower centrality value. So again three vertices 0, 6 and 7 have LCC prime DC of 0. So we break the tie in favor of the vertex ID. So vertex 1, 0 will get tentative rank 1, vertex 6 will get 2, vertex 7 will get 3. Then the smallest is next smallest is 1, so that is tentative rank 4. Then the next smallest is 2, tentative rank 5, then 2.56, 2.677, 7 and 3, 8. So there's no tie with the other centrality metric values. So now for the final rank, again since you have a tie here with 0 for LCC prime DC, you take the average of 1, 2 and 3, which is going to be 2. So that's the final rank for vertices 0, 6 and 7. Then there's no tie for the other vertices, so the final rank is same as tentative rank. So then you compute the difference in the ranking between the two centrality metrics. So the final rank for betweeners and the final rank for LCC prime DC, the difference. So in the first case it is 0, then 2 minus 2, 0, 5 minus 5, 0, 6 minus 7, negative 1, 4 minus 4, 0, 7 minus 6, positive 1 and so on. Now square these differences, so it is negative 1 square, 1 square. So sum of the squares of the differences is 2, and that's what we have in the formula. So this notation here is the sum of the square of the differences, so 6 times 2. So 1 minus 6 times 2 divided by its 8 vertices, so 8 times 8 square minus 1. So if you do the math, you get 0.98. That's a very high correlation coefficient, very close to 1. So this indicates that betweenness and LCC prime DC are very strongly correlated. And especially for rank-based correlation, we can see that if you want to rank the vertices based on betweenness, there's actually no need to really compute the betweenness values, because betweenness is very time consuming centrality metric to compute. On the other hand, we can compute the LCC prime DC values and rank the vertices based on the LCC prime DC values, and the ranking is going to be almost the same as that we would get with betweenness. As you can see, the correlation coefficient is close to 1. Okay. So now let us continue and do the concordance based correlation coefficient. So these are, again, the procedure is to write all the pairs of vertices and then compare them based on the two centrality metric values. So here, so these are the LCC prime DC values for vertices 0 and 1, the values are 0 and 2, and for betweenness the values are 0 and 2.33. So you have to check if 0 less than 2 is 0 also less than 2.33. Yes, so then the pair is concordant. Now for vertices 0, 2, these are the two centrality metric values for LCC prime DC, and these are centrality metric values for betweenness. So 0 less than 2.67, 0 less than 4, so it's concordant. Now there's only one discordant pair, which is the pair 2, 4. These are the LCC prime DC values of the two vertices, 2.67 for vertex 2 and 2.5 for vertex 4. The betweenness of 2 and 4 are 4 and 4.33. So you can see here 2.67 is greater than 2.5, but 4 is less than 4.33. So this is a discordant pair. Every other pair is kind of concordant. So if you now plug in the formula, it is the number of concordant pairs minus number of discordant pairs divided by the total number of pairs, which is n times n minus 1 over 2. So it's 8 vertices, so 8 times 8 minus 1 over 2 is 28, that's the denominator. So the numerator is 27 for the number of concordant pairs minus 1 the number of discordant pairs. So 27 minus 1 divided by 28 is 0.93, which is also very high and close to 1. Okay, so now let us do the Pearsons correlation coefficient. This is the formula for the Pearsons correlation coefficient. So as you can see, we need the average and then take the difference between the individual values and the average, and then square the differences as well as take the product of the differences. Okay, so as I said, most of the times we would need to compute the LCC prime DC values and use them to kind of analyze the betweenness. So we'll take the LCC prime DC values as the x variable and the betweenness as the y variable. Okay, so the average of the LCC prime DC values is 1.39. So now we'll compute the individual difference between individual values and the average. So 0 minus 1.39 is negative 1.39. 2 minus 1.39 is 0.61. 2.67 minus 1.39 is 1.28. 1 minus 1.39 is negative 0.39. So you do like this for all the vertices and then square these differences and then compute the sum of the squares of these differences, which is 11.78. So sum of all these squares of the differences. Now do the same thing for betweenness. Find average betweenness and compute the difference for the individual values and average. So 0 minus 1.99 is negative 1.99. 2.33 minus 1.99 is 0.34. 4 minus 1.99 is 2.01, and so on. So get the individual differences, square those differences and find sum of the squares of the differences, and then also take the product of the differences. So and then find the sum of the product of the differences. So in the numerator we have really the sum of the product of the differences, and the denominator you have the square root of the sum of the squares of the differences. So 19.17 divided by square root of 11.78, which is sum of the squares of the differences, times square root of 33.33, which is the sum of the squares of the differences for betweenness. And if you do the math, you get the Pearsons correlation coefficient to be 0.9675, again very close to 1. So what we observe is, with respect to all the three central correlation measures, you see a very strong correlation between LCC prime DC and betweenness. and now the Pearsons correlation coefficient very close to 1, we can proceed with the regression analysis. So like I said, we can plot the LCC prime DC values and betweenness in Excel. So these are LCC prime DC values, these are the betweenness. So we can, last time I showed how to plot in Excel, and then right click and find add a trend line, and that will give you the equation for the relating the two variables. So this is what you could see. Betweenness is 1.6269 times LCC prime DC minus 0.2728. Okay, so let me show in this video again how to get the Excel plot for people who are not still clear with that. So let us type the vertices LCC prime DC values between this. So this is for 0, 1, 2, 3, 4, 5, 6 and 7. So LCC prime DC values are 0, 0 0.2, 2.671, 2.53, 0, betweenness 0, 2.33, 4.33, 4.33, 5, 0. So all you have to do now is let me make it a little bigger. Okay, so highlight the LCC prime and the DC value and betweenness values and click on this chart. And on the chart menu, you can just use XY thing, and so this is the distribution. Okay, so you don't really need a title if you want to get notes. Just try to get rid of the title. Okay, so now you can right click, you can clear this one too. Now you can right click on the data point and click on add trend line, go to the options, you want to stay linear. Now go to the options and display equation on chart, display R square value on chart. Okay, so chart means this graph, the distribution of the X and Y axis. Alright, so this is the relationship that we have between LCC prime DC and betweenness. And you can see that the R square is 0.9357. So if you take a square root of this, you're going to get your correlation coefficient. 0.9673. And so once you get the equation relating betweenness and LCC prime DC, then you can go to the kind of regression analysis and try to or continue the regression analysis because this is also part of the regression and compute the standard error of residuals. Okay, now alright, so these are the actual LCC prime DC values, so that is your X values, and then using this equation that we just got, we can do the prediction of the betweenness values. So substitute the actual LCC prime DC values in this equation and get the predicted betweenness values. And now these are the actual betweenness values for the vertices. Now you see here, you may get the predicted betweenness as negative. That's okay, you can just stay with it. Of course, the actual values will be 0 or above, but this is just a prediction. So now to compute the standard error of residuals, we'll just keep the negative values as it is. Alright, so the next step is to normalize the actual and the predicted betweenness values. So we saw the procedure of how to do normalization. So what we need to do is square. So to normalize the actual betweenness, what we need to do is square these values, find the square root of the sum of the squares, and then once you find that square root value, divide each entry by that square root value. You'll get these numbers. Similarly, for this predicted betweenness, square these numbers, sum them up, and then find the square root of the sum of the squares and divide each entry by that square root value, and that's what we have here. So now you find the difference between the normalized actual betweenness and the normalized predicted betweenness values, and we call the difference as residual. Okay, and then take the square of the residual. So these are the square root of the residual, and then what you do is compute the square root of the sum of the squares of the residual. So you sum these square of the residual values and then take the square root of that sum, and in this case we'll get so that's called the standard error of residuals, and you're getting it as 0.18, which is still more closer to 0 compared to 1. Okay, so that means we can kind of say our prediction is reasonably accurate. Okay, so with that we'll stop this video.